let's talk about geometric series and do an example problem there. Okay, so we got definition of what a geometric series is. Well, I guess it's not a definition. It's this theorem 9.2. This is on page 669 of the textbook. We're going to be able to say that if we add up infinitely many terms of a specific geometric sequence, then it's going to come out to be a very nice value. So if we're given a sequence, we have a nice sequence here where k is bigger than or equal to 1, and also the absolute value of r is smaller than 1, then if we add up infinitely many terms, like we just take k from 1 until infinity, so we just add up terms over and over and over and over and over, just continually add up terms, then this is going to be this value if we add up infinitely many of these terms. So something that's happening here when we're adding up a sum, because that's kind of counterintuitive where we add up infinitely much stuff, but it's going to be just one number. It's not going to go toward infinity. What's happening here is that this value of r is going to be less than 1 in absolute value, so that means it's a fraction. So this number is larger than this number. If I multiply what I start with as a value by something less than 1 in absolute value, then this number is smaller than this one in absolute value. So as we go on in our sequence, terms are getting smaller and smaller and smaller and smaller. That's not exactly what's going on, but to show why this is true, actually they've got a nice little justification for why this is true in the textbook on page 669. But we explore this idea a little more in calculus, and I think it's probably a little more appropriate to talk about it at that point. But we sure can use this. If we've got a sum of infinitely much stuff, we can write it as a fraction, which is exactly what we want to do for these problems here. So write the repeating decimal as a fraction of 2 integers. Okay, so maybe it might not be so intuitive immediately that we're going to do something like this, but we can, right? If I've got a repeating decimal, I can rewrite this, right? It could be 0.55555, and so on and so on and so on, right? Forever and ever. Well, another way we could write that is 0.5 plus 0.05. That'd give you 0.55 plus 0.005, right? That'd give you 0.555 plus 0.0005 plus blah, 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 all the way on to infinity, right? Just infinitely many fives. Okay, so now what? Maybe we could write all these things as fractions, right? We know that 0.5, we know that's a half. So 0.05 would be 1 over 20. This would be 1 over 200. And then this would be 1 over 2,000. And so on and so forth. Well, now it's kind of starting to look like we want it to up here, right? Sort of. But it's not quite. Well, we can see that these all have a common factor in here, don't they? So this is 1/2 plus 1/2 times 1 over 10 plus 1/2 times 1 over 100 plus 1/2 times 1 over 1,000 plus so on and so forth. Well, now it's looking even more like it was, like we want it to, isn't it? So this is 1/2, just 1/2, and then we've got 1 over 2 times 1/10 plus 1 over 2 times 1 over 10 squared plus 1/2 times 1 over 10 to the third, and so on and so forth. So now that we have this, we can just compare it to the nice theorem, right? We've got a geometric sequence here. So our a value, that's this 1/2 here. I'm pointing off the screen. I'm just going to write this maybe down here in purple just to compare it, right? We got a plus a times r plus a times r squared plus a times r to the third plus blah, blah, blah. This is part of the theorem. This is going to equal, let me just write this. So this equals the sum from k equal 1 to infinity a times r to the k minus 1 power. So we can rewrite in blue our series. This is equal to, well, we just said that a is going to be 1/2. So we got the sum from k equal 1 to infinity, where a here is 1/2. And then our r is going to be 1/10 and k minus 1. And just, I mean, we can go through here and check and verify that we do get the right stuff. If I put in k equal 1, I ought to get this term. Well, if I put in 1, that's a 0, so anything to the 0 power is 1, so it is 1/2. If I put in 2, that's a 1, that's my second term, so it worked for those. If I put in 3, I'm going to have a 2 there, so that's, you know, pretty quickly verifiable. So we can write this as a geometric series with our nice notation. And what the theorem tells us is that if we have a geometric series, like we just showed that we did, we can find the sum by plopping our a value here and our r value here. I'm just going to rewrite this. That's a over 1 minus r. So this was the statement of the theorem, right? This was the theorem. So if you add all of these up, we can write it like this in summation notation, and the nice theorem tells us that this is what the sum is. Okay, and we can go ahead and just plop that in here. Oops, that was from earlier. Okay, so a is 1/2. 1 minus r, we got 1 minus 1/10. And now we just have to simplify this complex fraction, which isn't such a big deal. We got 1/2 over 1 minus 1/10 would be 9/10. So further simplifying this, we'd have 1/2 divided by 9/10. That's 10 over 18, which then simplifies to 5 over 9. So what we just showed was that the repeating decimal, 0.5 repeating, is equal to the fraction of the integers, 5 divided by 9. And I mean, we could check this in a couple of different ways. I think the easiest and most repeatable way to check this would be just to jam it in your calculator, right? Just do 5 divided by 9 in your calculator, and you're going to get 0.5 repeating.